Okay, not all relationships are obligatory. So a relationship may be partially participated in or fully participated in. Fully participation is where the relationship is obligatory. A partial participation is where the relationship is not obligatory. So in the example here of partial participation, a building may or may not have a postcode, but all postcodes must relate to one building. So for example, my house has a postcode, but maybe the derelict shed in the field does not have a postcode. So the relationship between postcode and building is one of partial participation. All postcodes must relate to a building. Not all buildings have postcodes. If a building has a postcode, it can only have one postcode in this relationship. Fully participation means that the relationship must exist. So in the example below, each student is either enrolled in 2 or 4 modules. There's GIS students, part-time students, GIS students here at Kingston enroll in 2 modules per year, full-time students enroll in the 4 modules. So each student must either be enrolled in 2 or 4 modules. A student cannot be enrolled in no modules in this example. This slide just shows some of the alternative cardinality notations that have been developed. Just bear in mind that these different notations exist and select one that is most appropriate to your needs and given your organisational requirements. Probably the commonest approach is to use the crow's foot notation at the top. It's often a good idea to include a key to your notation if you've got room on your ER diagram, just to make sure that people actually can clearly understand your notation and what your diagram is showing. Strong and weak entities. These are some ER diagrams show these. I don't think personally that they're really need to be included. However, you might well see these, and it's a good idea to know about them. So a strong entity has its own primary key. A weak entity's primary key is derived from other tables. So here we have an example of an authored book. In this example, the book, an authored book, or the authors to a book, there must be an author in the author table. So we need an author. So we've got a foreign key. So author ID in the authored book is the foreign key from authors table. The book ID is a foreign key from the books table. And the primary key is a composite key of author ID and book ID. So therefore, the primary key is derived from foreign keys from other tables, and authored book is a weak entity. And weak entities are displayed with the double box symbol. Another style symbol that you might see is the box with a diamond in, which define what are called associative entities. And that is a table that defines a relationship. Now, as we'll see, all end-to-end relationships end up getting defined as a table. So this is to a certain extent extraneous information, but you may well see it. The other one you may say is what's called an identifying relationship. And in this case, the entity's foreign key is also, in which case an entity's foreign key is also part of the primary key of that object. So, for example, in the authored book is also an example of an identifying relationship, because book ID is a foreign key, but it is also part of the primary key of that relationship. So authored book could be drawn as a double diamond identifying relationship. So we've just seen 3 different ways of drawing the authored book in an ER diagram. We can draw it as an identifying relationship, an associative entity, or a weak entity. Which we use depends on your personal, what you personally feel is required to display, whether you think that the additional information displayed is of use. Entity subtypes. It's often the case in the world that the attributes of 2 entities overlap significantly. And these are best modelled as parent-child relationships. So here's an example to do with phone calls. There are phone calls which have a source number and an identifier, a destination number, and perhaps the time of day in which the call is undertaken. Now, there are different types of phone calls, though. So there's regular phone calls, long-distance phone calls, and cellular phone calls. All those types of phone calls share the field source, telephone number, destination number, time of day, but have a different set of additional fields relevant to them. So a regular call just has a duration. A long-distance call has both a duration and a carrier, and a cell phone call has both land time and air time. So really what we want to do is to take the call object, or the call entity, and add on the extra attributes depending on which subtype of call we're talking about. This kind of relationship, these parent-child relationships, are not integral to the relational model and aren't modelled very well within the relational model, but is core to object models, and we'll meet these again later, both in this lecture and in the object modelling situation. So bear in mind that some relational databases may support entity subtypes. You may see them in an ER diagram, but they are not standard to ER diagrams or the relational model in general. Design issues. Okay. When you're drawing your ER diagram, just consider, I've already talked about these alternative notations. Here's this paper. These are some of the alternative notations collated by Song et al. Again, just bear in mind, choose one that's easily understandable within the context of the organisation that you're working in. Another issue can be size and complexity of ER diagrams, and indeed of UML class diagrams, which we'll meet briefly at the end of the lecture as well. So the larger your system, the larger your logical design diagram, and as the diagrams become larger, they become more cumbersome to manage and to understand. So you may need to, it may be desirable to split one large diagram into multiple smaller diagrams. Often, when you split it into multiple small diagrams, it's helpful to have a high-level overview diagram that shows the overall relationships at a large scale, at a high level within the system, and then also a set of diagrams that allows you to effectively zoom in to a lower level of detail within the various subsystems. As also mentioned, the same relationships between entities can be drawn in different ways. So it's often a good idea to try and prevent the complexity of the relationships becoming too complex. For example, if you've got 4, 5, 6 entities involved in a single relationship, that may actually be physically quite difficult to draw on a piece of paper, and it may be more sensible to split that those six entities in a single relationship into into more relationships between fewer entities. Also think about whether the reader really needs to know about weak and associated and identifying relationships, or is that something that's better dealt with at it's only needed to be known by, say, the computer developers, the developers of the system, and are not required by the sort of medium level managers who may be involved in the design process. So, do you need weak associative entities in your diagram? And that's the basis of ER diagrams. Now, ER diagrams were designed for relational database design, so need to be extended to include spatial entities and relationships. Geographic data type is an entity attribute. Entities may be represented as polygons, they may be represented as points. But what about spatial relationships? For example, topological relationships, X must be on Y. A water valve must be physically connected to a water main. X within Y. For example, a district council must be within the boundary of a county council. And things like X must not overlay Y. So district councils are independent entities that share common boundaries, so therefore no district council polygons can ever overlap. There also may be proximity relationships. For example, X must be within 20 kilometres of Y for some reason, whatever that may be. There are also perhaps relationships which vary with scale. And how do you include temporal relationships between entities in an ER diagram? ER diagrams are not designed to represent either scale relationships or temporal relationships. The standard way, or the emerging way, to display geographic data, or the geographic data types in an ER diagram, is to add pictograms to your diagrams of this additional symbology. So for example, here we've got an example of some various entities. So in a water network, we may have water valves, pipes and tanks. The valves may be point objects, the pipes are line objects, and the tanks, the water tanks, storage tanks, polygon objects. Physical objects in the real world, entities that we think about in the real world, may be in fact made up of multiple geographic features. So for example, we may have a river. We may be interested in rivers, the Thames, the River Lee, for example, the Hogsmill. But those rivers themselves are represented in our database by multiple lines, multiple river reaches in the terminology. So the River Thames may be, if we want, the River Thames itself may be made up of more than one feature in our table. So in that case, we can put a cardinality on the geographic pictogram. So a river is made of between one and many line objects. A country may be made between one and many polygons. So for example, a landlocked country like Switzerland may be a single polygon, whereas an island country like ourselves may be made up of many polygons. There are also maybe many continental countries have little areas that are embedded within other adjacent countries as well. For example, where I did some work, field work in the Pyrenees, there was an area of Spain which was an enclave totally enclosed within France. We can also use below that we see lines enclosed within a diamond shape, or a parallelogram, a sloping parallelogram, which may indicate that it is derived, that it is a derived variable. So in this case, the river, the Thames, is derived from a set of lines, and we could have put, of course, the 1 to n in there as well. So it might, so the River Thames is a derived spatial object that's derived from multiple line objects. Or indeed it may be derived in some other way from a single line object. We can also have multiple representations of the same object, perhaps at different scales. So, for example, the city object there, which has both a polygonal representation of a polygon, the urban extent, but also can be represented as a derived point, perhaps at smaller scales. And that derived point may well be the centroid of the polygon representation of the city. Finally, at the bottom, we have the star symbol, which means the geometry can be that any geometry might be associated. So, for example, we're outputting a report. We may have a report entity, and that report entity may be a report on a river, a line, or a report on a city, a polygon. And the final example, the exclamation mark, means that some kind of user-defined complex geometry or geometry with constraints is appropriate. We can also use pictograms to show relationships between, topological relationships between entities. So, for example, here, a route on the left-hand side, a route over a river network. We can use this sort of tree-like symbol to represent a line lying topologically on top of a network. Or on the right-hand side, a nested polygon relationship. So a region is a nested polygon relationship with a country. So we can use these pictograms to show the topological relationships between the various entities in space, spatial topological relationships. But that's really all I've got to say about entity relationship modeling. So just to finish off, a couple of slides on UML. So UML is the equivalent, well, it's the equivalent plus extras to entity relationship modeling, but for object-based logical modeling. A UML class diagram is very similar to an ERL diagram, but uses some different notation. And UML is a more general modeling language that models not just data relationships, but also things like user interactions, temporal event sequences, so a number of the other components of the data that are not represented in ER diagrams. This slide is not, sorry about the quality of it, but it basically just shows some of the different varieties of diagrams that modeling supports, including use cases, activity diagrams, temporal sequence diagrams, that's the kind of thing. And we'll be meeting UML a bit more in the object lecture later in the module. So one thing I want to point out here is that the object model supports subtypes, and if you remember, subtypes are not well supported or difficult to implement within the relational model. So In subtypes, the subclass, the lower entity level entity inherits functionality, attributes, constraints, methods, etc. from their superclass, the higher level entity. So in the example, we have a shape object which has a colour and a set of XY coordinates to define the shape. And the shape is a very general entity. The shape could be a circle, it could be a square, it could be a line, it could be a point. And then we have particular types of shapes, one of which would be a square. And the defining attribute or thing about a square is that it has sides of equal length. So we can add in so a square has an additional side length attribute in addition to its colour and its string of XY coordinates. So a square is a shape plus some additional attribute, constraints or methods. This is the key for the object model diagrams used in the arc map, used to describe the arc map, arc objects, or the arc objects data model. Arc objects is the underlying library from which ArcGIS is built and which you can use to, you can program with to create customized applications in ArcGIS. Won't worry about the details here, but simply see that the triangular relationship is a type inheritance, which is the superclass subclass relationship. Really, it's just showing you here that there's a different there's a different set of symbology and a different set of relationships that can be displayed in UML diagrams that can't be displayed in ER diagrams. An example, and here's one, that's the key, here's an actual example, and this is the core geodatabase model arc objects diagram. And in this diagram we can see that a table and a geodata sets are types of data set. A feature data set is a type of a subclass of the geodata set. A feature class is a subclass of an object class. In no way do I expect you to understand particularly this diagram, but just to appreciate that they are the alternative, the equivalent. So UML class diagrams are the equivalent of UML diagrams, but for object-oriented modeling. So, to summarize, conceptual design basically provides a system overview for all that's relevant to all users and designers and decision makers in relation to the system. The logical design is effectively an on-paper design that should fully specify the relationships, entities, their attributes, and the relationships between attributes independent of any particular database system. Entity relationship modeling and UML are alternative approaches for implementing logical design or undertaking logical design. ER, entity relationship modeling, is the older system and has, as we've seen, quite a loose notation. But just because it's a loose notation doesn't mean that notation, the notation that you decide should be used loosely. UML, which is a more recent development, has a much more standardized notation. Just to finish off, I want to mention CASE tools. CASE stands for Computer-Aided Software Engineering. And what these CASE tools are CASE tools take ER and UML diagrams that have been drawn in particular software systems and takes those designs and automatically implements a physical design directly from the ER, or a partial physical design directly from the ER and UML diagrams. So this saves quite a lot of time It potentially saves a lot of time in system development, because you don't need to manually implement the parts of the logical design, or the logical design in the database management system, the particular database management system you're doing it. It is automatically done, and then you can go in and just do the additional changes required for to implement the physical design fully, and we'll deal with that next week. Okay.